2C, truth in measurements and calculations. 214, significant introducing digits. A scientist's integrity and professional reputation depend on the accuracy and lack of ambiguity in his observations and reports. If a scientist's observations and data cannot be reproduced by others using the same instruments and techniques, he loses the regard of his peers, along with the potential for future research funding. Scientists are careful to report their data only to the precision warranted by the instruments or methods used. Precision is indicated by the kind and placement of digits reported in the data. These digits are called significant figures or significant digits, SDs. Only the digits that are certain based on the instrument scale calibrations, and one estimated digit, in tenths of the smallest subdivision, may be reported as significant digits. Consequently, the last, rightmost significant digit is the estimated digit when recording measured data. Zeros are added as placeholders, before or after the significant digits, as appropriate, to locate the decimal point. 215 rules for determining significant digits in data. How can we tell which digits are significant when we read someone else's data? This is important to know, especially if a mathematical operation is to be performed using the data. Rules have been developed which make this process fairly easy. Each rule below is followed by one or more examples. Rule 1 SDs apply only to measured data. The following numbers are not measured data. They are considered to be exact, and therefore SDs are not applicable. Counted or pure numbers. 2, 1 dozen, PAI, root. 2. Ratios that are exactly 1 by definition. 60s, man. 100 centimeters m. Rule 2. All non-zero digits in measured data are significant. 324.4 meters, 4 SDs. 62 C, 2 SDs. Rule 3. All zero between non-zero digits in measured data are significant. 100.3 millimeter, 4 SDs. 7.025 p.m., 4 SDs. Rule 4. For measured data containing a decimal point, all zeros to the right of the last non-zero digit, trailing zero, are significant. 30.0 the 3 SDs. 16500 L, 4 SDs. All zeros to the left of the first non-zero digit, leading zeros, are not significant. They are merely placeholders for the decimal point. 0.040 meters, only last 2 digits are SDs. Rule 5. For measured data, lacking a DCML pint, no trailing zeros are significant. 1500 meters, 2 SDs. We cannot tell if this measurement was estimated to the nearest 100 meter, 10 meter, or 1 meter. Therefore, we can be assured only that at least the 2 nasio digits are SDs. SD Rule 2. Scientific notation, see Appendix G, shows only significant digits in the decimal part of the expression. 1.50 x 10 cubic m, 3 SDs. This notation indicates that the measurement was estimated to the nearest 10 meters. In this textbook, a decimal point following the last zero indicates that the zero in the ones place is significant. 1500.m, 4 SDs. This measurement was estimated to the nearest 1 meter, so all 4 digits are SDs. Mathematical operations with measured data. 216 calculated precision. Why do we need to know about significant digits? Let's calculate the density of a stone with a mass of 5.85 gram and a volume of 43 cubic cm. Density, chat mass over volume, chat 5.8 Ig over 4.3 cubic cm, about shashir 1.360465116 gram per cubic cm. The result as displayed indicates that the density calculation is precise to at least a billionth, 10⁻⁹ power, g-char cube cm. However, the volume was known only to the nearest tenth, 10⁻⁴ power, cube cm, and the mass only to the nearest hundredth, 10⁻² power g. If we compare the precisions of the mass, the volume, and the calculated density, we find that the density displayed above has a far higher precision than the measured data. A scientifically valid calculation should have a precision that is about the same as the precisions of the contributing factors. Scientists often perform calculations with measured data to derive other data, so they have established some additional rules in order to make sure that their results do not have more or less precision than the original data. The rules for mathematical operations that follow are convenient for high school work, but they do not give the scientifically acceptable precision in every case. Scientists doing research must determine the precision for each calculation based on approval statistical methods for a given kind of calculation and the kind of measured data used. 2.17 Math Rule. 1. Adding and subtracting measured data. A. Measured data must be the same kind of data and have the same units before they can be added or subtracted. You cannot add apples and oranges. B. The sum or difference of measured data cannot have greater precision than the least precise measurement. Round results to the place value of the estimated digit in the least precise quantity. 2.18 Math Rule. 2. Multiplying and dividing measured data. A. The product or quotient of measured data cannot have more SDs than the measurement with the fewest SDs. Round results as necessary. The density that we calculated in subsection 2.16 should be rounded to 2 SDs, or 1.4 g cubic cm, since the volume, 4.3 cubic cm, has only 2 SDs. B. The product or quotient of measured data and a pure number should not have more or less precision than the original measurement. Examples: 7 times 1.75 centimeter, 12.25 centimeter, not 12.3 centimeter. 1.35 centimeter divided by 7, 0.19 centimeter, not 0.193 centimeter. 2.19 Math Rule. 3. Compound calculations. You should know how to efficiently use a modern scientific calculator. Multiple math operations can be completed simultaneously using nested parentheses and other functions. Compound calculations involve 2 or more simultaneous math operations. A. If the operations in a compound calculation are all of the same kind, either addition, subtraction, or multiplication, division, complete the operations simultaneously using standard order of operations before rounding to the correct significant digits. Math Rule 1. This practice eliminates excessive rounding errors. See example 2-6. B. If a solution to a problem requires the combination of both addition, subtraction, and multiplication, division operations, rounding the intermediate solutions may introduce excess rounding errors into the final answer. 1. For intermediate calculations, you should underline the estimated digit in the result and retain at least one extra digit beyond the estimated digit. Drop any remaining digits without rounding. 2. Round the final calculation to the correct significant digits according to the applicable math rules, taking into account the underlined estimated digits in the intermediate answers. Carefully examine example 2-7 on the next page to see how this works. 2.20 Math Rule, 4 angles and trigonometry. A. Angles in the SI are measured in derived units called radians. A radian, rad, is the plane angle that subtends a circular arc equal in length to the radius of the circle. See figure 2-24. There are 2 pay radians in 360 degrees. Standard degree units for angles are not part of the SI, nor are they metric. In this textbook, angles may be expressed in either degrees or radians, depending on the application. Angles measured with a protractor should be reported to the nearest 0.1 degree. B. The process for converting between degrees and radians is discussed in Appendix G, but is summarized here. Degrees to radians. Theta, radians. Theta, degrees, times pi over 180, radians to degrees. Theta, degrees times 180 over pi. These conversion factors are definitions, so the new angles retain the number of SDs of the original measurement. C. Report angles resulting from trigonometric calculations to the lowest precision of any angles given in the problem. For example, if an angle given in the problem is stated in whole degrees, then any angles resulting from calculations should be expressed to the nearest whole degree. D. For simplicity, Assume that trigonometric ratios for angles given in this textbook are pure numbers, so SD restrictions do not apply. Consequently, the standard deviations of trigonometric problem solutions will depend on the precision of the non-angular data given in the problem rather than the precision of the trigonometric ratios.